the inclined plane without friction. Previously, we dealt with horizontal surfaces, like this right here. In that case, the normal and mg were always along the y-axis and were equal if there was no acceleration along that axis. Now, examine a surface that is not horizontal. This non-horizontal surface is the inclined plane. The normal is always perpendicular to the surface, so in this case it's pointing off at an angle. mg is always directed downward, but now they are neither parallel nor perpendicular to one another. Previously, the horizontal and vertical, that is the x and y axes, were used. That worked because the problems always resulted in an acceleration that was along one of those axes. But for the inclined plane, the acceleration is not horizontal or vertical. It will slide up or down the incline, and we're going to say it doesn't lose contact with the surface. That would make the problem way too complex. In this case, the block can accelerate only along the surface of the plane. It will slide down in the absence of an applied force. Why? Well, that's gravity. But it will go up if it is pulled with an applied force. So the x and y axes are rotated to line up with the surface of the plane. Consider the direction as positive down the incline along the x-axis. Consider the normal force is also in a positive direction, but this time along the y-axis. This assignment is consistent with a standard Cartesian coordinate system, even if it is rotated. Another reason the x and y axes are rotated is to simplify the math, especially when the friction force is added. So let's assume we have an applied force pulling it down the incline, where friction here is in the opposite direction. By rotating the coordinate system, we only need to resolve one force, mg, into its x and y components. What if the axes weren't rotated? Right? What if you're more happy with just having your standard, non-rotated Cartesian coordinate system? How many forces would have to be resolved into x and y components? Assume the x and y axes are in the conventional horizontal vertical setup, indicated by the red dashed lines. Here's your y-axis, here's the x-axis. Three forces, the normal force, the applied force, and friction, would need to be resolved in their components along these axes. That's 3 times as much trigonometry, always something to be avoided. The only force not aligned with the rotated coordinate system is mg, the force of gravity, over here. It makes an angle of theta prime with the rotated y-axis. These types of problems typically give the value of theta, the angle of the incline. To resolve mg along the rotated x and y axes, we need to find the relationship between theta prime and theta. Create the red triangle as shown. Label the third angle in the red triangle as alpha. So here's our triangle. Since the angles in a triangle add up to 180, and this angle is 90 degrees, that means alpha plus theta equals 90 degrees. Alpha and theta are complementary angles. Now examine the angles at the upper left corner of this red triangle. Since there's a right angle between the y-axis and the surface, right here, that's a right angle, the angle alpha in the triangle complements the angle theta prime from the y-axis. So we can say that theta prime plus alpha equals 90 degrees. We also showed earlier, previous slide, alpha plus theta equals 90 degrees. So we set those two equal to each other and we find that theta prime is equal to theta. The gravitational force mg over here has components into the surface y and along the surface x, and will affect the force equations in both cases. To determine its impact, it needs to be resolved into its x and y components along the rotated axes. So this would be f sub y, this would be f sub x. Please notice how this line here, completing that mg triangle, it's parallel to the rotated x-axis. As done earlier in this chapter, trigonometry will be used to resolve mg into its components along the rotated x and y axes. F sub x is opposite theta and was drawn parallel to the rotated x-axis, so the sine function will be used. Sine theta is opposite over hypotenuse. Sine theta equals f sub x over mg. So what we have is f sub x equals mg sine theta. F sub x is a component of mg on the x-axis, the rotated x-axis, and will act to accelerate the box down the incline. Next, solve for the y component of the gravitational force. F sub y is adjacent to theta, so the cosine function will be used. Cosine theta is adjacent over hypotenuse, or f sub y over mg, so in this case, f sub y equals minus mg cosine theta. We put the minus sign in here because it's in the down direction. F sub y is a component of mg on the y-axis and equals the magnitude of the normal force, which of course is like that. The gravitational force has now been resolved into x and y components along the rotated axes. F of x is positive because it's in the same direction as the expected acceleration, and Fy is negative because it's into the incline. How is this different from when forces were resolved along the non-rotated coordinate system, where the x-axis was horizontal and the y-axis was vertical? Just like this, right? We had x here and y there. In the non-rotated coordinate system, the force and acceleration components use the cosine function in the x direction and the sine function in the y direction. That's reversed now. So here we have f sub y equals minus mg cosine theta, because it's heading down here into the incline, and we have f sub x is a positive mg sine theta, as it's in the same direction as the acceleration down the incline. One way to remember this is sine slides. mg multiplied by sine theta gives the force that accelerates the object down the incline. Now that mg has been resolved into its two components along the x and y axes, the normal force will be added and the total frictionless picture will be shown. Normal force, mg, and let's see what happens on the next slide. We'll apply Newton's second law to the forces on each rotated axis, and we'll start here with the y. In this case it doesn't really matter, but I like to get in the habit of doing the same thing here. The sum of the forces in the y direction equals m acceleration y, but it's not moving up and down on the incline. In other words, it's not going like this. So that acceleration is 0. Substitute in our forces. We have the normal force minus mg cosine theta is equal to 0. So the normal force is mg cosine theta. In the x direction, we have the sum of the forces is m sub ax. So mg sine theta equals max, masses go out, and a sub x is g sine theta. A sub x does not depend on the mass of the object. And once again, just emphasizing this, the sum of the forces in the y direction is 0 since the block is sliding down the incline without bouncing.